Hey everyone, welcome back. Today we're going to be taking a deep dive into something kind of old school.
Oh,
Ripple tanks.
ripple tanks.
You
Okay.
know those shallow tanks of water they use in like physics class
Yeah.
to show wave behavior?
Right.
We're diving into an article all about a digital ripple tank simulator.
Okay.
Now I know you're thinking sounds a little dry, right?
Maybe.
But trust me, this is way more than just water.
Oh, yeah. Ripple tanks are fascinating. They let us actually see how waves interact,
Right.
which is something we can't normally see.
Yeah.
And it's how everything from light and sound to ocean waves, it's how they behave.
Okay, so let's paint a picture here for everybody.
Okay.
Imagine like dropping two pebbles into a still pond.
Right.
You get those expanding circles, the ripples.
Yep.
But what happens when those ripples, when they collide?
Yeah, that's when things get really interesting.
Yeah.
And that's what ripple tanks help us to understand.
So a ripple tank, I mean, what is it exactly?
Basically, it's a shallow tray of water with a light shining above it.
Oh,
And when
wow.
you make waves in the water, right,
Yeah.
they make shadows on the screen below, so you can see those wave patterns.
So it's like a giant watery light show
Yeah.
revealing the secret life of waves.
Exactly.
Like, how do you actually create these wave interactions in the ripple tank?
Well, one common way is to use two dippers that vibrate in the water,
Okay,
and each one acts as like a separate source of waves.
got it. So it's like having two tiny synchronized swimmers creating like a wave ballet in the tank.
I like that analogy. So as those dippers create the circular waves, right?
Yeah.
Those waves, they eventually intersect, they overlap.
Yeah.
And that's where the magic of interference comes in.
Okay, hold on. Interference.
Yeah.
That sounds a little ominous. Are these waves like fighting each other?
Not fighting, no, more like collaborating. You
Uh-huh.
see, when waves overlap, they don't just pass through each other,
Okay.
they combine their energy, and it's what we call superposition.
Okay.
And that leads to these really amazing patterns of constructive and destructive interference.
All right, let's break that down.
Sure.
What does constructive and destructive interference actually look like in the tank?
So in areas of constructive interference,
Yeah.
the waves, they reinforce each other,
Okay.
creating like bigger crests or deeper troughs.
Okay.
Imagine two friends pushing a swing together.
Uh-huh.
They amplify the motion.
Right.
And in the ripple tank, those areas appear as like bright spots on the screen below.
So constructive interference is like a wave party.
Uh-huh.
Everyone's in sync, boosting each other's energy.
Exactly. Now, on the other hand, destructive interference,
Right.
that happens when like a crest from one wave meets a trough from another wave,
Okay.
and they cancel each other out.
Ah.
So you get this flat area where the water's still,
Oh, well.
and those show up as dark spots on the screen.
So destructive interference is like two waves trying to do opposite things at the same time, resulting in like a stalemate.
Perfect analogy. And those areas of cancellation where the water's calm,
Yeah.
they're called nodes.
Mm-hmm.
And the bright spots where the wave action's amplified, those are antinodes.
Nodes and antinodes is like the wave version of peaks and valleys on a map.
Yeah, I like that.
But our source material mentions
Yeah.
that these patterns, they aren't random.
Right.
There's a whole mathematical relationship going on here.
Absolutely.
Right.
So the position of those nodes and antinodes
Yeah.
depends on a few key things,
Okay.
like the distance between the wave sources,
Uh-huh.
the wavelength of the waves,
Okay.
and something called the path difference.
Okay, I think I'm following so far.
Good.
The path difference.
Yeah.
Break that down for me.
So path difference is basically the difference in distance that each wave travels from its source
Right.
to a specific point in the tank.
Okay.
Imagine you and a friend are racing to a finish line,
Okay.
but you have to take a detour. That adds like an extra 100 meters to your route.
Okay. Yeah.
That extra distance is your path difference.
Got it.
So longer detour, path difference.
Okay, so a longer detour for one wave creates a path difference.
Right.
But how does that impact the interference pattern, like what we see?
Okay, so here's where it gets really interesting.
Okay.
If the path difference is a whole number of wavelengths,
Mm-hmm.
meaning one wave traveled a whole wavelength farther than the other,
Yeah.
they'll arrive at a point in sync, creating constructive interference.
It was like two runners, like perfectly synchronized,
Yeah.
hitting the finish line at the exact same time.
Precisely. But if the path difference is half a wavelength,
Okay.
or any odd multiple of half wavelengths,
Right.
the waves arrive out of sync.
Okay.
One wave's crest will hit the other wave's trough,
Mm-hmm.
and they cancel each other out. Destructive interference.
So in our race analogy, that would be like one runner tripping right before the finish line,
Yes.
completely messing up the synchronized finish.
Exactly. And our source material actually dives into some specific examples and calculations to show this.
All right, let's unpack those. Walk me through one of the examples.
Okay, so in point 10 of the source material,
Yeah.
they describe a point in the tank where the distance from source S1 is 4.5 wavelengths.
Okay.
And the distance from source S2 is also 4.5 wavelengths.
So the path difference is 0.
Yes.
They both traveled the same distance.
Right.
But what does that mean for the interference pattern?
Well, since the path difference is 0,
Yeah.
the waves arrive perfectly in phase,
Okay.
meaning their crests and troughs line up perfectly.
Mm-hmm.
This leads to constructive interference, and you get a bright spot, an antinode, as the source material describes.
Okay, so 0 path difference, perfect harmony, bright spot.
Exactly.
Got it. What about an example where there ion path difference?
Okay, let's look at point 12.
Okay.
Here, the distance from source S1 is 5 wavelengths,
Mm.
and the distance from source S2 is 5.5 wavelengths.
So now we have a path difference of half a wavelength.
You got it.
What happens then?
Because the path difference is half a wavelength.
Yeah.
The waves arrive out of phase.
Okay.
One wave's crest will hit the other wave's trough,
Right?
leading to destructive interference.
A node, that dark spot where the waves cancel each other out.
Yep.
So the exact position of those nodes and antinodes in the interference pattern
Yeah,
depends on that precise relationship between path difference and wavelength.
exactly. It's pretty fascinating how something as simple as the distance a wave travels can have such a big impact on the overall pattern.
It's like this delicate dance between distance and wavelength, all playing out in this little tank of water.
And what's even more remarkable is that this whole principle of interference, it doesn't just apply to water waves.
Oh, really?
It governs how all sorts of waves behave, from
Wow.
sound waves to...
Hold on, we got to dive into that. But first, a quick recap for our listeners. Ripple tanks give us a visual way to grasp wave interference.
Yeah.
But the mind-blowing part is that this principle governs how all sorts of waves behave, not just water.
Absolutely. But we'll explore all the incredible implications of that after a short break.
Right after this. All right, so beyond the ripple tank, you mentioned sound waves earlier.
Right.
What's going on there?
Well, think about what happens when you have, like, two speakers playing the same music. The sound waves they make, they spread out, just like the water waves in the ripple tank.
Yeah.
And they interfere with each other.
So we'd get those same patterns, like nodes and antinodes,
Exactly.
but with sound instead of water.
Exactly. So you'll have areas where the sound is louder
Okay.
because the waves are constructively interfering.
Right.
And areas where the sound is quieter or even silent.
Well,
As well as that destructive interference.
So that's why sometimes when I'm walking around my apartment with music playing, like the volume seems to change depending on where I'm standing.
Exactly. You're moving in and out of those zones of constructive and destructive interference.
It's like an auditory heat map of sound intensity created by those waves interacting.
Yeah, it's really cool.
I've noticed that at concerts too, like certain spots in the venue
Right.
sound way better than others.
And that's because concert halls and recording studios, they're carefully designed using these principles of wave interference.
Oh, wow.
You know, sound engineers use those principles
Yeah.
to create the best listening experiences.
That's incredible to think about, like these invisible waves
I know.
shaping our auditory experience.
Mm-hmm.
It's like a hidden symphony happening all around us.
It really is. And you know, it's not just sound.
What else?
Light waves interfere too.
Oh, yeah.
Yeah, think about those iridescent colors you see
Okay.
on soap bubbles or on like the surface of a CD.
Oh, yeah. It's like a rainbow explosion on a tiny surface.
It is. It's beautiful.
I always wondered how those colors appear.
That's light wave interference.
Oh, wow.
So the thin film of the soap bubble or the grooves on the CD, they cause light waves to reflect and interfere with each other.
Okay.
And depending on the thickness of that film or the spacing of the grooves, certain wavelengths of light are amplified,
Okay.
while others are canceled out.
So the colors we see are determined by, like, which wavelengths of light survive that interference battle.
Exactly. It's like nature's own light show.
Wow.
Created by this precise interplay of light waves.
Okay, this is seriously blowing my mind.
It's cool, huh?
Like, wave interference is the secret ingredient behind so many everyday things.
It really is.
But if we can understand these interference patterns and predict them, can we also, like, manipulate them?
That's a great question, and it leads us to some really groundbreaking applications.
Okay, like what?
Like noise-canceling headphones.
Oh, really?
They wouldn't exist without a deep understanding of destructive interference.
Wait, really? how do those work? I've always wondered.
It's not magic, it's science.
Okay.
So noise-canceling headphones have these tiny microphones
Yeah.
that pick up the incoming noise,
Right.
and then they generate sound waves that are perfectly out of phase
Oh,
with
wow.
that noise.
So they're fighting fire with fire, like sound with sound.
Yes. And when those opposing sound waves meet,
Yeah.
they cancel each other out through destructive interference,
Wow.
creating those pockets of silence that we all want in a noisy world.
It's like having a personal sound engineer in your headphones,
Uh-huh.
constantly analyzing and like manipulating the sound waves.
That's a great way to put it.
And this goes beyond just noise cancellation, right?
Oh, yeah, for sure.
Like what else?
Engineers are looking into ways to use constructive interference.
Okay.
Make these highly focused beams of sound almost like a sonic laser.
Whoa, that would totally revolutionize everything.
Yeah.
From concert sound systems to like public address systems. No more annoying loudspeaker announcements blasting through the whole airport terminal.
Exactly. You could target the sound
Yeah.
only to the people who need to hear it.
That's incredible. So like the potential applications are huge.
They are.
And as we understand wave interference better,
Yeah.
our ability to harness its power grows too.
Absolutely.
It's amazing how something as simple as waves interacting
No, right?
can have such a huge impact on our world.
And we haven't even talked about how wave interference is crucial in technologies like ultrasounds.
Oh, right. Ultrasound. And what was the other one?
Wireless communication.
Those are big deals. We can't wrap up without talking about those.
Right.
So how does wave interference, how does it power those technologies?
Okay, so ultrasound, it uses high-frequency sound waves
Okay.
to create images
Yeah.
of your internal organs and tissues.
They're like sonar systems, but for our bodies.
Exactly. So they send out these pulses of sound waves,
Right.
and those waves reflect off of different structures in your body.
And those reflections create the images.
Well, it's a bit more complex than that.
Okay.
The ultrasound machine analyzes not just the reflections,
Yeah.
but how those waves interfere with each other
Oh.
after they're reflected.
And so the interference patterns are like clues
Yeah.
that reveal the shape and makeup of the tissues.
Precisely. And by analyzing those patterns, the machine can tell the difference between different types of tissue,
Wow.
detect abnormalities, even create 3D images.
It's amazing how something as subtle as wave interference
I know, right?
can unlock so much information about what's going on inside us.
And it's not just about seeing inside the body.
Oh, right. What else?
Ultrasound's also used for therapies,
Like what?
like breaking up kidney stones.
Oh, wow.
Or delivering targeted drug therapies.
Okay, so I've got sound waves being used to create images
Yeah.
and even manipulate matter inside the body.
Uh-huh.
What about wireless communication then? How does wave interference come into play there?
Okay, so wireless communication relies on radio waves, which are a type of electromagnetic wave.
Right.
And just like any other wave,
Right.
radio waves can interfere with each other.
So that's why sometimes like my Wi-Fi signal gets weaker or just drops out completely.
I can't.
It's like a battle of the waves.
Yeah, so think about all the devices in your home emitting radio waves.
Okay, like what?
Like Wi-Fi routers, smartphones, laptops,
Yeah.
even your microwave can add to the interference.
So my kitchen is a war zone of competing waves.
In a way, yes, but engineers are always working
Yeah.
on ways to minimize that interference
Okay.
and optimize those wireless signals.
That sounds like a pretty tough challenge,
It is.
given all the different frequencies and signal strengths bouncing around.
It is, but they use all these sophisticated techniques to filter out unwanted signals,
Okay.
amplify the desired signals,
Right.
even adjust the direction of radio waves to improve your reception.
So it's like this constant game of wave manipulation, trying to create the perfect flow of information through the airwaves.
Yes. It's all about understanding how waves work.
Yeah.
And then using that knowledge to make technologies that improve our lives.
This has been amazing.
It's been fun.
I never realized how much wave interference shapes our world,
Uh-huh.
from the music we hear
Right.
to the images we see
Yep.
to the technologies that connect us.
It really is a fundamental principle of physics
Yeah.
that affects so much of our modern world.
But before we finish up,
Yeah.
I have one last question.
Okay, shoot.
We've talked about all these amazing applications.
Yeah.
But are there limitations? Like, are there things we can't do with waves,
That's a great question.
even with what we know now?
So while we've come a long way
Yeah.
in understanding and manipulating waves,
Mm-hmm.
there are still so many mysteries and challenges ahead.
Like what? What are some of the frontiers of wave research?
Well, one area that's really active right now
Okay.
is finding ways to make wave manipulation even more precise and powerful.
Okay. Scientists are working on developing new materials and techniques
Uh-huh.
to control things like the direction,
Okay.
the focus, and the intensity of waves
Wow.
with even greater precision than we can now.
So it's like refining our wave manipulation toolkit, going from blunt instruments to fine-tuned surgical tools.
That's a great analogy. And these advancements could lead to huge breakthroughs in fields like medical imaging, telecommunications, even energy production.
This has been an incredible journey.
It has.
I feel like I've gained a whole new perspective on how the universe works.
It's been a pleasure exploring these concepts with you.
But before we sign off, I want to leave our listeners with something to think about.
Okay.
We've seen how scientists and engineers are already using wave interference to do amazing things. But what if we could take it even further?
Like how?
What if we could use wave interference to manipulate matter itself?
Wow. That's a fascinating thought. What if we could create objects?
Move objects, even teleport objects, using the power of wave interference.
That's something to ponder. Thanks for joining us on this deep dive into the world of waves.
Thanks for having me.
Keep those brain waves rippling, and we'll catch you next time on the deep dive. Teleporting objects with waves, huh? That'd be something else.
It would.
But even without teleporting, it's amazing what we can already do with wave manipulation.
Yeah, it shows how powerful it is to understand these basic physics principles.
It's like learning a secret language to interact with the world.
Exactly.
Speaking of unlocking a hidden language,
Yeah.
I think we should go back to our ripple tank for a sec.
Okay.
And revisit those examples from the source material.
Sure.
Just to make sure we're getting everything we can out of this deep dive.
Good idea.
It's easy to get caught up in all the amazing applications,
Right.
but those ripple tank experiments really show us the basics of wave interference.
Absolutely. They lay the foundation.
Let's go back to those points in the source material
Yeah.
where they calculate the path difference and how it relates to the interference pattern.
All right.
Like point 13, for example.
Okay, so in point 13, the distance from source S1 to a point in the tank is 6 wavelengths.
Okay.
And the distance from S2 is 6.5 wavelengths.
So a path difference of half a wavelength again. I'm noticing a pattern here.
You're picking up on it. Whenever that path difference is half a wavelength or any odd multiple of half wavelengths, you get destructive interference.
Right, because the waves are out of sync.
Exactly.
One's crest hits the other's trough, and they cancel out, making a node.
Yes, one of those dark spots in the tank.
And the source material backs that up.
It does.
Point 13 is a dark spot. Destructive interference.
That's right.
Okay, makes sense.
Good.
But what about those points where the path difference is a whole number of wavelengths?
Okay.
Like point 11.
All right, point 11, let's see.
The distance from S1 is 5.5 wavelengths. And the distance from S2 is also 5.5 wavelengths.
So in that case, the path difference is 0.
0. So the waves arrive perfectly in sync.
Exactly. Their crests and troughs line up perfectly.
Leading to constructive interference.
That's right.
And a bright spot in the tank.
Yes, because the waves are amplifying each other.
Boosting their energy.
And if we check the source material, point 11 is described as a bright spot, just like we thought.
It all makes sense now.
Good.
The ripple tank really helps us see these complex wave interactions.
It does. It makes something invisible, tangible.
And it connects those visual patterns to the math behind it all.
Absolutely.
Okay, last question about the ripple tank examples.
Okay.
What about those points where the path difference isn't a whole number or a half number?
Good question.
What happens then?
Then you get something in between constructive and destructive interference.
All right.
The waves, they don't perfectly reinforce or cancel out.
So you might see a dimmer spot or weaker wave.
Yeah, something like that.
So it's like a spectrum of interference. From full reinforcement to full cancellation with everything in between.
That's a great way to put it. It's not always black and white.
This deep dive has been incredible.
It has.
We've explored how ripple tanks work.
We have.
Uncovered the secrets of wave interference and discovered how it affects sound, light, and all these technologies.
It's been a great journey.
And, most importantly,
Yeah.
we've seen how understanding these basic principles can spark our imagination.
Definitely.
Lead to new questions, new discoveries.
Absolutely.
Who knows what other applications of wave manipulation are out there?
Yeah, who knows what the future holds?
Maybe we'll even figure out how to teleport those objects.
Maybe one day.
Thanks for joining us on this adventure into the world of waves.
It's been a pleasure.
We hope you've learned something new and are as amazed by ripple tanks and wave interference as we are.
Me too.
Until next time, keep exploring, keep asking questions, and keep those brain waves rippling.